Hi everyone, welcome to a video for the Dell Technologies Associate Data Science EMC course, and this video is going to go through big data applications and the ecosystem. So let's get started. So within this video we're going to discuss the definitions of big data characteristics and structure, the sources of big data, and understanding the business drivers for big data. So 4 big topics we're going to discuss. So what are your thoughts on what big data is? Is there a threshold to classify the data you're working with as big data? Well, Dell EMC defined this as data which is above and beyond the data in which your organisation currently has infrastructure and tools to support, consume and analyse. So the big data itself isn't set as a certain size, so it's not how much data you can fit in a box, for instance. It's looking at your company and whatever task and project you're currently doing and working out whether the data can be organised within your infrastructure and tools. If it can't, then it becomes big data. As Forbes say, big data is a collection of data from traditional and digital sources inside and outside of the company that represent a source for ongoing discovery and analysis. And information is the oil of the 21st century, and analytics is the combustion engine, Gartner said. So that's a small definition of what big data is. So data sets so large they break traditional IT infrastructures. Big data doesn't only signify a human volume of data, but also a range of different complex data types and structures with an increasing volume of unstructured data. So some of the things we're going to discuss today, we're going to discuss the types of data you could have. So with that, a lot of the data that we will classify as big data in itself is unstructured, so it could come from a range of different sources which we're going to look at. It's generally it's generated and changes rapidly, so a lot of the data that we use itself is dynamic, and it often comes from a diverse array of sources. The significance of big data to big business is huge. So Netflix, for example, we're going to go through a couple of examples, suggests that your next movie rental on the actual screen. So obviously everyone's used Netflix at some point, and if you haven't, please do, because Netflix is good. Go through it and you'll see that it's categorised different films for you to watch and different series for you to watch based on common opinions of your own browsing and surfing, but also common opinions of different people who have watched similar things to you. So you might watch, you might watch Breaking Bad, and then you might find that it's linking it straight to Better Call Saul, and that's because obviously they're kind of interlinked with the series, but everyone that's watched Breaking Bad generally would have watched Better Call Saul as well. So if you're going to look at big data and looking at how it combines with something like Netflix, even little tiny things like that can push sales, and it can push the engagement of clients and that sort of thing. So another example is a dynamic monitoring of embedded sensors in bridges to detect real-time stresses and long-term erosion. So here's a completely different example, looking at a bridge, and what this bridge does, like looking at the picture, it has sensors all around the bridge and it records data from all of these sensors continuously, and then it feeds it back into an algorithm or a data analyst environment, and then there's people that can look at this data, analyse it, and then work out where the stresses and long-term erosion points will be. Obviously this is something that is really important to the bridge itself, to make sure it's safe and it's long lasting and all those sort of things. Okay. Another example, hospitals predicting health ahead of time and reducing hospital admissions. Obviously we're going through the COVID stuff at the moment, so a lot of big data will have been done, and it will look at different past trends of different countries and different analysis points, and it'll be getting as much data as it possibly can from anywhere and trying to use that data to benefit the whole system. And then finally, retailers analysing digital video streams to optimise produce products and display layouts and promotional spaces on a store-by-store basis. So analyses digital video streams to optimise products. So it looks at your viewing habits It looks at where you go after you've clicked on certain items, and then from that it will build an environment which, for you, when you access it, it gives you the best environment to make you buy stuff or to make you do certain things. Obviously, algorithms such as this, there's ethical considerations to do as well because they're tracking us. However, from a business side, it can be invaluable to get them sales and to push up and drive resources. So, how much data do we actually use? So the amount of data we use every day is similar to this. So Facebook processes 0.5 petabytes every single day. Google processes 24 petabytes every single day. And surveillance cameras around the world produce 413 petabytes every single day. So you can see on the little chart below what a petabyte is. So obviously we generally work on our PCs in gigabytes and megabytes. You've got terabytes, which is pushing to server level, and then petabytes is going beyond and beyond. So a quick example is 2.5 years of continuously watching is around 1 petabyte. So 413 is 1,000 plus years of continuously watching surveillance cameras every single day. Okay, so there's a lot of data out there that we can use or we can access in order to do certain things and track. So obviously surveillance cameras in a football stadium, for instance, could be tracked, and you could look at where the crowds of people are going to be to improve safety and all that sort of stuff. So, and another thing as well, the surveillance cameras, for an example, is unstructured data. So all the data you're getting through is through video and sound and images, so it's really hard to categorize that data. So there's different things we have to put in place to allow that to happen as well. So processing this data, like we just discussed. So big data also extends the processing of analysing capabilities of conventional IT infrastructures and software systems. It not only needs a high scalable architecture for efficient processing and analysis, but also requires new and innovative technologies and methods of processing. So we need to find new ways of processing this big data because it's so new and it's so advanced compared to where we really are. These technologies typically use platforms such as distributed processing, massive parallel processing, and machine learning. So generally, that's the process that would be undertaken when using big data, essentially. And you've got a little picture there just to kind of show what happens. So you've got the data, the big one, which has got all the data processing. You've got the analysis stage, and then it's being passed down into information and machine learning stage, which we'll discuss in a bit more detail at some point. So the characteristics of big data. Within data analysis, big data can be categorized using the 3 V's. These are volume, velocity, and variety. So we're going to discuss the 3 V's, which I would like to mention the 4th one, which I kind of, not just me, but in data analysis, the value of big data sometimes is forgotten, even though it could be the most important thing. So you should always focus on value when undertaking a data science project, and making sure that the structures you put in place and the way you've done it allows you to come out with a finished product which would help the problem that you started off with. So there's no point looking at volume, velocity, and variety if the final outcome from it doesn't help the problem you started off with. So value is really important. It can bring in a lot of new technologies and projects, and generally ran to work with these technologies, data analysis, and cannot work that way. So a lot of things that IT brings in, big data conflicts with. So big data itself doesn't generally work within conventional IT systems, and therefore we need to put different things in place to allow big data to work. You should always start by understanding the business problem first, which is really, really important. You then need to solve the business problem with the analytics problem. And you need to solve it in order to then understand the data tools and capabilities you need to solve the problem. So the problem, and then the approach taken, not the approach taken and then look at the problem. So a lot of companies and a lot of big businesses will have approaches in place already, or structures or methods of doing things. However, your problem won't fit into the approach that is already been set out for you. You need to look at the problem from a holistic standpoint and then take an appropriate approach based upon that. Okay? So, the characteristics of these 3 V's then. So you've got volume, and the word big in big data refers to the masses volume of data, organisations and witnessing an ever-increasing growth in data of all types, such as transitional-based data stored over the years, sensory data and unstructured data streaming in the form of social media. So that's volume, size, is there enough data for adequate samples? Velocity, so refers to the rate in which data is produced and changes, and how the rapid generation of data must be processed to meet the business requirements. And variety refers to the diversity in the formats and types of data. Data in general is generated by numerous sources in various structures and non-structured formats. So these 3 different V's, you've got volume, which is size, you've got velocity, which is ever-changing data, and then you've got variety, looking at the different types of data, and then trying to form some form of structure based upon that. So, some technologies advancements such as wearable consumables, for instance, currently generate enormous amounts of data, personal data that can help companies assess our health. It is estimated that 2.5 quintillion bytes, so we just quickly go back to the quintillion bit here, you've got petabytes, exabytes, zettabytes, yottabytes, and then it's quintillion bytes after that. We're up to quintillion bytes of data are created around the world, and this number will double in 1.2 years. So the velocity of data itself is advancing so fast, and the volume of data we're collecting day by day is increasing day by day. So apart from this data, the petabytes of data generated by commercial airlines, credit cards, transitions, and almost every sector every second generates data. You watching this video, and you download it through Teams, will be generating data. So everything you're doing online, or everything you're doing going to a shop, or you're doing anything, is generating data. So again, some quick examples to show you how much data is being done. Amazon sells on average 600 items per second. So imagine how much data that's recording. YouTube users view 12 years of video in a single day, and the list goes on. This data would fill approximately 10 million Blu-ray discs, which when stacked would measure 4 Eiffel Towers, one on top of each other, every single day. Self-driving cars in the future will generate 2 petabytes of data per hour. So obviously self-driving cars aren't quite a thing yet. If Mr. Musk and Tesla get the finger out, then in a couple of years we might see self-driving cars which will generate this level of data, and this level of data obviously from that point needs a structure in place in order to support it. So it's estimated suggests that 40 zettabytes of data will be created by later this year, an increase of approximately 300 times from 2005, most of which has been generated in the last couple of years. So in the 15 years up to this point, it's increased 300 times. And then you're probably thinking 150 times of that is over the last 2 to 3 years. So even though the advancement of technology is going so fast, it's probably going to go faster and faster, and more big data is going to be made because of it. So the characteristics of this big data. So considering these statistics then, that explain the rate in which data is being produced. Every 60 seconds there are 98,000 tweets, 695,000 status updates on Facebook, and hundreds of thousands on Google searches. It is estimated that 150,000 gigabytes a second is the rate of global traffic by 2020. This traffic must be processed quickly to generate real-time insights. So processing data is a real-time method. So we need to obviously keep on track, and we need to produce analytical states and environments to allow this data to come through and us to evaluate and investigate it straight away. There's no point investigating data from 3 years ago, because generally, depending on what business you're in, it'll change so much. So this real-time data can help researchers and businesses make valuable decisions that provide strategic competitive advantages and returns on investment, i.e. resources and time. So with variety then, a characteristic of big data, organisations face the challenge of managing, merging, and analysing the differences and varieties of data in a cost-effective manner. The combination of big data from various data sources and in various formats is key to the changing in big data analytics. So the way it's changing, the way it's pushing, the way we can look at trends is really, really important. So, considering these examples of combining many changing records of the particular patient with various published medical research to find the best treatments. We've got varieties of data sources which include doctors' written notes and prescriptions, medical imagery in laboratories, patient data, machine-generated sensors, social media posts, and less patient-specific information such as emergency care data, news feeds and articles. All them things could work together as a variety in order to help predict some things about the hospital, some things about the actual patients themselves, and it should allow all that range of data to get a holistic overview on the problem that you've got to solve and allow you to come up with solutions of how it could be solved or it could be helped. So for a big data scientist, there is amongst the vast amount of arrays and data opportunities by discovering associations and understanding patterns and trends within data. So big data analytics has potential in this example to improve care, save lives and lower costs. So it has a massive potential in lots of different things. Okay. Big data characteristics, data structures, so we discussed this already in one of the previous modules. However, I just thought it was quite good just to go over some of the key points of big data. So at the bottom you've got unstructured data. So generally that's stuff like images and videos, and 80% of data is unstructured. Then you've got quasi-structured data. This is generally to do with patterns that form based on clicks or things that you do. So if you go to a website, for instance, and you click 3 or 4 different things in a certain order, then that becomes quasi-structured data. You've got semi-structured data, which is textual data with discerning patterns, and generally that's stuff like XML, which is kind of structured but not completely structured. And then finally you've got full structured data, which is generally databases and CSV and Excel files and everything that can be transformed straight into that format. It's easier to analyse at a structured level. However, unstructured data and quasi-structured data can be really, really important to finding out more qualitative views on that data. So all this sort of data working together is really important. So we've got all this data, and then we need an ecosystem in order to support the data. So as the new ecosystem takes shape, there are 4 main groups of players within this interconnected web. These are data devices, data collectors, data aggregators, and data users and buyers. So, organisations and data collectors are realising that data can be gathered from individuals containing intrinsic value, and as a result, a new economy has emerged. As this new digital economy continues to evolve, the market sees the introduction of data vendors and data cleaners. Sorry. So, within the data environment itself, you've got a range of devices which could collect data, and here's just some examples. So cell phones, GPSs, iPods, ebooks, video games, cable boxes, RFI chips, computers, lots of different things. Data devices shown in here are basically part of SensorNet, gathering data from multiple locations and continuously generating new data about new data. So it's recording something, and then 2 minutes later it's deleting it and recording it again, and you're building up trends and trends and trends. So for each gigabyte of new data created, an extra petabyte of data is created about that data itself. So it might be recording GPS locations in your watch, and then that data itself is then being transferred as new data to Google Maps, and Google Maps is collecting all of the data. So for each part of data that we're recording, then you're creating a lot more data on top of that by analysing it and collecting the data in a certain way. So again, even though you're not collecting so much data to start off with, it can then turn into that amount. So here's some examples. This example is just looking at an intelligence system within a game. So for instance, if you play a game on Steam or on the Xbox or your phone, and then you do something within that game which allows you to turn up the difficulty, for instance. If you turn up the difficulty within the game, it might record some data throughout the platform, so your phone and Steam, which tells the publishers that you might prefer games in a certain way. So that information itself can then help marketing and tracking. It might also store locally stuff like gaming habits and opportunities for upselling. So it might sell you products such as shirts on the favourite games based upon how many hours you've played the game. So a lot of stuff it's recording like that through devices could be really good for resources in building good marketable campaigns and publicising certain products. A couple more examples: the smartphone. Smartphone provides rich sources of data. In addition to this, it records data such as internet usage, SMS. The metadata can be used for analysing traffic patterns by scanning the density of the smartphones in locations to track the speed of cars. So you could use a smartphone, you might not think about it, but Google Maps records your location all the time unless you turn it off. So you could go onto Google Maps and it will literally tell you patterns of where you've been. And if you've been somewhere in the last week, it will show you your map and it'll show you where you've been and where you stopped and how long you were there for and that sort of thing. So some of this data that we're recording is being used for other things as well. And then finally, a quick one, a retail shopping loyalty card. The reason we have loyalty cards is not to make you go back to that shop necessarily, it's to record your purchase products. So if you're buying certain things at a certain time, then the company knows to advertise that certain thing certain time, maybe to you or to other people, in order to push sales and push the marketability of it. Then after we've got the devices, we've got the collectors. So data results from a cable TV, for example, track the shows a person watches. With TV channels somewhat will and will not pay for on demand, the prices someone is willing to pay for premium TV content is important. So looking at a TV provider, they will track what you're watching, and they will collect certain amounts of data, and they will customize your environment based upon that. Retail stores tracking the path of customers taking through their store while pushing a shopping cart with an RFID chip in it, which is just a little chip that records data, so they can gauge which products get more foot traffic using geospatial data collected from an RFID chip. So it will look through when you're buying pizza, will you buy beer which is next to it if I move the beer over towards where the pizza is, rather than having to go to the other side of the shop to get it. So obviously some of this data which is being collected by the collectors can be really, really important. Then we've got data aggregators. So these organisations compile data from the data devices and the usage patterns collected by government agencies, retail stores and websites, and in turn they can choose to transform them and package the data as products to sell to list brokers. These products may want to generate marketing lists of people who may be good targets for specific ad campaigns. So for instance, they could be an advertising company which looks at all of the different sales of a certain product at a certain time frame around Christmas. They could then package this as data and information for products, and then they could sell it to big companies such as Amazon or Argos, who can then use the data in order to inform their choices that they're going to make based upon these things. Rather than carrying out the data analysis themselves, data aggregators take it all and then act as like a middleman. And finally, but probably most importantly, we've got the data users and buyers. These are the people that actually use the data. So the groups directly benefiting from the data collection and aggregated by others within the data value chain. So these could be companies such as, or not companies, but services such as law enforcement, media, banks, governments, individuals, delivery services, marketers, employers, and private investigators and lawyers. So all of these different things and different companies and people and services could use the data at the final stage. Here are some quick examples. So retail banks acting as data buyers may want to know which customers have the highest likelihood of applying for the second mortgage or a home equity line of credit. To provide input for this analysis, retail banks may produce data from a data aggregator. This kind of data may include demographic information about people living in specific locations, people who seem to have a specific level of debt yet still have solid credit scores, or other characteristics such as paying bills on time and having savings accounts. All these different things to retail banks could be really, really important. This can be used to infer credit worthiness, and those people who are searching in the web for information about paying off debts or doing home remodeling products. Obtaining data from these various source aggregators enables a more targeted marketing campaign, which would have been more challenging before big data due to the lack of information and high performance technologies. So there's just an example of how from start to finish it could be used. So ecosystems then. This emerging big data ecosystem illustrates that the kind of data and the related marketing dynamics vary greatly. These data sets can include sensory data, text data, structured data and social media. With this variety in mind, it is worth recalling that these data sets do not work well with traditional enterprise data warehouse methods, or EDWs, which were architected and streamlined reporting and dashboards to be centrally managed. Instead, big data works with problems and projects require different approaches to succeed. So, communications, media and entertainment, financial services, healthcare, social media and Internet of Things could all include different elements of requirements in order to support the big data. So from a data scientist point of view then, so we'll take it back to the start, this emerging discipline of data scientists represents the combination of several existing disciplines, such as statistics, mathematics, data visualization, machine learning and computer science. All them different things fall into the category of being a data scientist, with the final goal of extracting meaningful data. In simple terms, it is an umbrella technique used when trying to extract insight and foresight from data. This combination enables insight data mining as well as foresight predictions. So as a data scientist, you might be looking at all of them different things in order to predict, in order to create a data analytics problem based upon a business problem that you've been given at the start. So we've got business intelligence then, the last little topic we're going to discuss in this video, versus data science. So business intelligence reports on what has happened. Business intelligence tends to provide reports, dashboards and queries on business questions for the current period in the past or in the past. So business intelligence is looking at what's happened and then forming some reports, etc. based upon it. Data science predicts what will happen, so it's looking to the future. Data scientists tends to use disaggregate data in a more forward-looking, exploratory way, focusing on assessing and presenting states and enabling informed decisions about future projects. So you can see from the picture there, we've got business intelligence and time. Generally, data science will have a bigger business value, but it will also take more time. Here are some quick examples on what generally are the differences. I'm not going to go through all of them, but you'll have these slides as well. So typical techniques and data stores, they have a certain range of typical techniques that are used within business intelligence, and it generally uses things like structured data, traditional sources and manageable data. And then with predictive analytics and data science in itself, you're generally looking at structured and unstructured data, many types of sources, very large data sets and optimized predictive models and that sort of thing. The important thing on this slide, I think, is the bottom question. So from a business intelligence point of view, you might be asking what happened last quarter, how many did we actually sell, what is the problem, in which situation did we sell this, and where was the problem. Predictively, you're going to say, what if? What's the optimal scenario for our business? What will happen next? What if the trends continue? Why is this happening? So you're looking at more forward-thinking questions, and you're trying to identify how you can then help the problem and take a proactive look on that issue. So the typical architecture for business intelligence, this is a standard architecture. So you've got data sources, and you've got your data warehouse, in fact, the departmental warehouse, and then you've got your EDWs which store the data, and then they produce generally dashboards, reports and alerts towards the end. The requirements then of data scientist projects, they need their own workspace that is a purpose built for experimenting with data with flexible and agile data architectures. These are generally things like Apache Hadoop and Greenplum servers, and you have generally a different architecture to work with. Most organisations still have data warehouses that provide excellent support for traditional reporting methods and simple data analysis activities, but unfortunately have a more difficult time supporting more robust analysis. This is generally to do with the size of the data and the variety of it. There were 4 main steps then for getting data flow right and including the data scientist fitting into the process of getting data to analyse on the projects themselves. So step 1 is, this is taken from the book as well, the EMC book. For data sources to be loaded into the data warehouse, data must be well understood, structured and normalised with appropriate data types defined. All this kind of centralised enables security backup and failover over high security critical data. What this means is that data sources need to be loaded into the data warehouse. Step 2, as a result of this level of control on the EDW, more local systems may emerge in the form of departmental warehouses and local data marts that business users create to accommodate their need for flexible analysis. So after we've created and we've added to the normal data warehouse, you might start to build other systems which allow this data to be used. And then number 3, after it's in the data warehouse or your new environment, data is read by additional applications across the enterprise for Power BI reporting purposes. These applications are high priority operational processes getting critical data feeds from the data warehouse and repositories. So again, you've put the data in the warehouse, you've created new environments for people to work with, and then step 3 is people are starting to work with them environments. And then finally, step 4, at the end of the workflow, data scientists, users get data provisionally from their downstream analytics. Because users generally are not allowed to run custom or intensive analytics on product databases, we need to create our own different versions of these environments. Generally, you wouldn't use some of the data analytics tools within the environment which is already there, just to make sure you don't break it. So many times these tools are limited to in-memory analytics on desktops. However, if we use stuff like cloud, it can be much more expanded from that point. So the video's taken 32 minutes. I know I might talk quite fast, but I just wanted to get like an overview, and I didn't want it to take like 2 hours for you to go through. So key topics covered in this presentation are big data and its characteristics, sources of big data, evolving analytics architecture, and the role of the data scientist. Again, I've added some further reading to this, and you've got the book, the EMC book, to go through as well. But hopefully that just helped you and re-jogged your memory about some of the things that we discussed. On the next video, we're going to be looking at the data analytics lifecycle. Thanks.